Hello all, welcome back. In the previous lectures we were discussing about the estimation of evaporation. Two methods we have already seen, energy balance method and the aerodynamic method. In the energy balance method we have considered the important factor which is influencing evaporation as heat energy from the sun. And in the second method, that is the aerodynamic method, we have considered the wind velocity and the specific humidity. But we know when we are talking about the process of evaporation, all the three, that is the wind velocity, specific humidity and also heat energy, all the three factors are very important. So, in this lecture, that is today's lecture, we will be discussing about a combined method which incorporates all these three factors which are influencing evaporation. Let us move on to the lecture. As I already told, energy balance method that incorporates heat energy, and in the aerodynamic method it incorporates humidity and wind velocity. So, we need to have a method which combines all the three factors together for finding out the evaporation. So, we will be deriving a method which is the combination of the two methods which are already seen, that is the combination of energy balance method and the aerodynamic method. In the energy balance method, what we have considered? We have considered the heat energy from the sun, that is Rn, heat radiation that can be measured. But the two other terms Hs and G, sensible heat and the heat lost to the ground surface, were very small. Those values we have already neglected. The equation which is used in the energy balance method, or the equation which is derived by the energy balance method, is given by this expression: E is equal to 1 by LV rho W Rn minus Hs minus G. In this we have neglected the terms Hs and G, and finally we got the expression for evaporation due to net radiation as Rn divided by LV rho W. The complete detailed derivation of this particular equation we have seen under the topic of energy balance method. Now, we should understand that the two quantities have been neglected, that is the sensible heat, that is heat lost to the atmosphere, and also the heat lost to the ground. But when we are talking about the heat lost to the atmosphere, that cannot be neglected. So, but at the same time it is difficult to quantify also, that is the sensible heat flux or Hs is very difficult to quantify. So, how can we incorporate this particular term even though it is difficult to quantify? That is the next question. Heat is transferred by convection through the air overlying the water surface. We have seen two processes, transport processes such as convection and convection. And in the previous lecture, that is while deriving the expression for aerodynamic method, we have seen the vapor flux and also the momentum flux, or the vapor transport or the momentum transport is taking place through the transport process termed as convection. In the similar way, heat is also getting transferred to the atmosphere, that is through air, by convection only. And at the same time we have seen water vapor is also transferred by convection. So, because of these two processes, water vapor is transferred by convection and also heat flux is also taking place due to convection. This implies that the vapor heat flux and the sensible heat flux are proportional to each other. What is vapor heat flux? Given by the expression LV mv dot, and the notation which we are using for heat flux is Hs, that is nothing but our sensible heat. So, since these two processes are taking place because of convection, we can assume that the same mechanism, that is heat transfer and also the vapor transfer, is taking place due to convection. Both of these processes are due to convection. So, what we are going to conclude that the vapor heat flux and the heat flux can be considered to be proportional. That is, LV m dot V and Hs can be considered to be proportional to each other. Hs is directly proportional to LV mv dot. You should clearly understand why we have considered like this, because both of these processes, transport processes, are due to convection. We can write Hs is equal to beta LV mv dot. This beta is known as Bowens ratio. So, beta can be written as Hs divided by LV mv dot. So, you look at the equation, we are having sensible heat incorporated here and we are having the vapor heat flux, that is the expression is LV mv dot. What we have assumed, we have considered these two processes, we know these two processes are taking place due to convection. So, accordingly, since both are taking place under same transport phenomena, we can consider these two are proportional to each other. That way, we have considered a coefficient of proportionality as Bowens ratio and beta is written as Hs by LV mv dot. Now, in the energy balance equation, we have considered, we can put only the ground heat flux G is equal to 0. When energy balance equation was finalized, we have considered Hs and G equal to 0. Here what we are going to do, we are going to incorporate sensible heat Hs by means of Bowens ratio. So, there only remains another term related to heat flux, that is the heat lost into the ground surface, that is G. That can be, since it is of very small amount, that can be neglected. It is not going to affect the final expression for evaporation. So, how our equation will be looking, Rn minus Hs minus G is equal to LV mv dot. In this, what we are going to do, we are going to substitute G is equal to 0. So, it will be Rn minus Hs is equal to LV mv dot. Now, what we are going to do, we are having the relationship between Hs and LV mv dot, right, in terms of Bowens ratio. Hs equal to beta LV mv dot. So, for Hs we can substitute beta LV mv dot. The terms can be readjusted and we will get the expression for Rn as 1 plus beta multiplied by LV mv dot. So, here in this you can see we haven't neglected the sensible heat, we have incorporated the sensible heat in terms of Bowens ratio. Even though directly we have not considered Hs, indirectly beta is dictating the effect of Hs. Now, next question is how to estimate the value corresponding to beta. In the case of, we are just going back to Thornthwaite-Holtzman equation, that is the equation which is derived based on aerodynamic method. While developing the Thornthwaite-Holtzman equation, we have considered two transport processes and combined together. Those two transport processes are related to vapor transport and momentum flux. So, there we were considering vapor flux and momentum flux are due to same transport processes, that is due to convection. In the similar way, here also we are going to couple two transport processes for the estimation of beta. That is, we are going to couple the transport equations for vapor and heat. That is, vapor flux and heat flux are mainly due to the process of convection. So, these two processes will be coupled together. These two equations will be coupled together for the determination of beta. So, we can write the vapor transport mv dot as minus rho a kW dQV by dz, and also the sensible heat Hs as by the, it is due to the process convection, and we can write it as minus rho a Cp Kh dt by dz. So, here in this case Cp is the specific heat at constant pressure, Kh is heat diffusivity, T is the temperature. So, you can compare the equation, mv dot is directly proportional to specific humidity gradient and also heat flux is directly proportional to temperature gradient. So, that specific humidity gradient is dQV by dZ and temperature gradient is dT by dZ. So, other terms are coming. Due to convection, that particular process is written as a, that is in the case of vapor flux, it is mV dot is proportional to particular gradient, that is the humidity gradient, and in the case of heat flux it is something related to temperature. So, it is related to temperature gradient. And after that you can look at the equation. Proportionality coefficient is taken by these two terms in m dot v and these three terms in Hs, that is in the case of this sensible heat. Now, what we are going to do, these two processes are proportional to each other. Since both of these are taking place due to the same transport process, that is due to convection. So, this sensible heat flux and also the vapor flux both can be taken as proportional to each other. That is what we are going to do in the next step. And for that also, since there are gradient we are taking between two planes, we are considering two planes. One is near to the water surface and the another one is just above that. Two planes we are considering Z1 and Z2. And what we will be doing, using the measurements of QV and T at two different levels, Z1 and Z2, we can calculate the corresponding values. And also the different distance between Z1 and Z2 is taken in such a way that the transport rate is constant between these two levels. And also we can assume that the temperature variation and also the this what you call specific humidity variation, all these are linear process. This vapor flux is given by this equation and also sensible heat is given by this equation. And what we are going to do, we have already mentioned that these two processes are proportional to each other. So, we can consider in that way. Hs by mv dot ratio we are taking. So, just substituting in that, certain terms will get cancelled, rho a will get cancelled, minus rho a divided by minus rho a will get cancelled. Now, we can look at the denominator and numerator. We are having two gradients, temperature gradient and specific humidity gradient. Temperature gradient we can write dT by dZ and specific humidity gradient dQV by dZ. So, dT by dZ can be written as T2 minus T1 divided by Z2 minus Z1. That is why I told you the distance between two layers which we are considered Z1 and Z2 should be very small, then only we can assume the linear variation. Then regarding dQV by dZ, we can write it as QV2 minus QV1 divided by Z2 minus Z1. After that, what we will do, we will be substituting this in this particular equation of Hs by mv dot. So, here when we are substituting these Z2 minus Z1 in from these two terms will get cancelled and we will get the expression Hs by mv dot is equal to Cp Kh divided by Kw T2 minus T1 divided by Qv2 minus Qv1. Now, for getting the Bowens ratio, we need to, that is we know already beta Bowens ratio is given by Hs divided by Lv m dot v. We already have Hs divided by m dot v from the previous slide given by this equation. So, what we have to do, we need to have some Lv, latent heat of vaporization, in the denominator here in the left hand side, Hs divided by Lv mv dot. For that, we will be dividing the entire expressions, that is on the left hand side of the equation and right hand side of the equation, by latent heat of vaporization. So, we are going to divide this equation by Lv. So, we will get the equation to be like this, Hs divided by Lv mv dot is equal to Cp divided by Lv Kh by Kw T2 minus T1 divided by Qv2 minus Qv1. Here you can see left hand side is representing the Bowens ratio beta. Now, what we have to do, we know the expression for Qv. From the water vapor dynamics we have seen, we are taking this equation, Qv is given by 0.622 E by P. and we are having two terms QV1 and QV2. QV1 can be written as 0.622 E1 by P, QV2 can be written as 0.622 E2 divided P. We can take the difference between QV2 and QV1, it will be taking this form 0.622 E2 minus E1 by P. The same question will arise here also, why not P1 and P2? So, we are considering the distance between these two layers which we are considered in such a way that there is not much variation, or the pressure at the level Z1 and Z2 are more or less equal. That is why we are not considering P1 and P2 separately, we are considering only P. So, this we can substitute here in the equation. So, when we substitute in this particular equation, this equation will be taking the form Hs divided by Lv mv dot as Cp divided by Lv, Kh divided by Kw, T2 minus T1 divided by 0.622 E2 minus E1 divided by P. We can make some rearrangements of the terms. So, then Hs by Lv mv dot will be looking like this: Cp divided by 0.622 Lv, Kh divided by Kw, P multiplied by T2 minus T1 divided by E2 minus E1. So, you look at the left hand side is Hs divided by Lv m dot V, that is nothing but our beta, Bowens ratio. So, this is the expression for beta. So, you look at the terms which are contained in the equation for beta. Cp 0.622 Lv, Lv can be computed by means of the empirical equation which we have discussed earlier. Kh and Kw are known values, coefficients, and the atmospheric pressure or small p can be calculated. T2, T1, E2, E1, either temperature can be measured, and the temperature at one level will be measured, and T2 can be calculated from the Labstrate equation. Even E2, all these things can be vapor pressure can be measured or calculated by using the corresponding formula. So, we are getting the value corresponding to beta if we are making use of this equation. So, beta is given by this equation, and what we are going to do? We are going to club certain terms together. Beta is written as gamma T2 minus T1 divided by E2 minus E1. What is gamma then? Gamma is termed as psychrometric constant. So, whenever you are dealing with evaporation, you may come across the term psychrometric constant. It is nothing but gamma, that is given by Cpp divided by 0.622 Lv, Kh divided by Kw. So, this is the equation for Bowens ratio. Now, according to Priestley and Taylor method, this is a common method, combined method used for finding out evaporation. What they have assumed, they have conducted so many evaporation experiments, and they have found out a combined expression for evaporation. So, Priestley and Taylor assumed that Kh by Kw can be taken as 1, then gamma will be taking the form of Cpp divided by 0.622 Lv. So, pressure we can measure, latent heat of vaporization we can calculate, Cp is known to us. So, gamma can be obtained. Once gamma is obtained, gamma multiplied by T2 minus T1 divided by E2 minus E1 will be giving you beta. Now, we are considering the two levels in such a way that what we have done in the case of aerodynamic method, same consideration we are going to do here also. Level Z1, one is at the evaporative surface, that is on the water surface. From the water body evaporation is taking place, the surface of that water body is considered as the level 1, and the level 2 is considered at a distance away from the water surface, at a distance of Z2 as we have denoted. This gap should not be too high, so that our assumptions are, it should be taken in such a way that our assumptions of linear variation should be valid. Now, weighted estimate of evaporation. Why we are telling weighted estimate? We are considering, we are going to consider both energy balance method and also the aerodynamic method. So, the weighted estimate of evaporation is given by the evaporation by, we are going to combine together evaporation rate ER computed from the rate of net radiation, that is nothing but our energy balance method. Energy balance method, we have derived the equation, and also the second one, evaporation rate computed using aerodynamic method. Now, combined evaporation equation is given by E is equal to combination of evaporation due to net radiation and also evaporation due to aerodynamic method. Evaporation due to net radiation is incorporating the heat energy, and the aerodynamic method incorporates the case of wind velocity and also the specific humidity. So, that is given by the equation E is equal to delta divided by delta plus gamma ER plus gamma divided by delta plus gamma EA. ER is representing the evaporation due to net radiation and EA is the evaporation due to aerodynamic method. Now, we have discussed about some term gradient delta when we were discussing about the saturation vapor pressure curve. The gradient of the saturated vapor pressure curve, that is given by delta, delta is given by DES divided by T. So, it is given by 4098 ES divided by 237.3 plus T whole square. So, if we are having the temperature and the corresponding saturation vapor pressure, we can calculate the gradient of that particular saturation vapor pressure curve. That gradient is required while calculating the evaporation due to combined method. And here in this equation, gamma is psychrometric constant and delta is the gradient of saturation vapor pressure. We are having the expression for calculating ER, evaporation due to net radiation, and also EA is the evaporation due to evaporation calculated by using aerodynamic method, that is due to wind velocity and also specific humidity gradient. That way EA also can be calculated. So, the total evaporation capital E is given by the combination of ER and EA. Gamma is given by this equation and ER is given by Rn LV rho W, and EA, evaporation due to aerodynamic method, is given by B multiplied by ES minus EA. Now, this is the most accurate method for calculation of evaporation because it incorporates both the aerodynamic method and also the energy balance equation, both the energy balance and the aerodynamic method, and at the same time energy balance method was ignoring sensible heat. Here we have incorporated the sensible heat also. So, all together this equation will be giving you an accurate estimate of evaporation. Now, when we are talking about evaporation over large water bodies, Priestley and Taylor, this method is termed as Priestley and Taylor method, a combination method for determination of evaporation. They have conducted experiments in different types of lakes, and evaporation is determined using energy balance method and also aerodynamic method. They have conducted experiments, experimental measurements they have done, they have calculated the evaporation due to energy balance method and also aerodynamic method. Then what they have found out that the observation from the study states that energy balance consideration largely governs the evaporation rate. That we know, if sunlight is not there, what is the energy source for this process? So, energy balance method incorporates the net radiation coming from the sun, and that is the predominant factor which is influencing the second part, that is due to the vapor transport, due to wind and also specific humidity gradient. It was found that only 30% of the first term is coming from the aerodynamic equation. So, combined evaporation can be written as E is equal to alpha multiplied by delta plus gamma ER. So, what is alpha then? Delta gradient of the saturation vapor pressure curve, gamma psychrometric coefficient, and ER is the evaporation due to net radiation. Alpha is nothing but the value is 1.3. How this value is coming out to be 1.3? That is the weightage for the second term. Weightage for the second term, that is due to aerodynamic case, is coming out to be 30%, and weightage of the first term is 100%. The weightage given to evaporation due to net radiation is 100%, and we are considering 30% of that is the only contribution from evaporation due to aerodynamic method. So, combined together they have taken a factor alpha and put the combined equation as alpha multiplied by delta divided by delta plus gamma ER. So, here ends this topic of combined method of evaporation.